Okay. So, let us consider two things. First thing to be considered is what is called as a, if I measure, to consider temperature alone, the temperature thermal part of it, if I go and measure the temperature as a function of height. So, we are saying that vertical convection happens as a result of thermal forces, which means there is a temperature difference. So, what is the temperature difference that will result in vertical movement of air masses? So, which means that I need to know what is the temperature profile as a function of height. So, I need to know what is the temperature as a function of height. So, let us say that this axis is temperature, it is also the ground, this is height z, yeah. So, which means this is ground, but I also have a temperature axis here. So, what will be the temperature profile on the earth's surface? First, this is environmental data, earth's surface. Normally, if I go outside now, what is likely to be the temperature profile? Okay. So, the temperature profile turns out, if you go out now, the temperature profile is generally like this, approximately, to a certain height. Beyond that it will change. So, this height beyond that it will change is the somewhere in the troposphere it changes. Beyond that point it becomes the temperature profile changes for other reasons, but that is the region or not, we are not interested in that region because it is very far away. We want what is happening very close to the surface of Earth. Now, let us say this is at 2 p.m. What happens as we go closer to the sunset, when sun, this is happening because you have this kind of behavior, mainly because this radiation is, during the daytime there is radiation, the radiation heats up this soil or land faster than it heats the air. So, radiation directly heats the soil, and when this is hotter, as a result this temperature of the soil is very hot. You can see that normally when you are in summer times or in the peak daytime, the land is very hot. You can see it much hotter than what the temperatures in the air are. So, as a result of which there is a positive temperature gradient in this direction. The air above the surface heats up from the soil, it does not heat from the sun directly, because the soil heats much more rapidly than the sun, because if you look at radiation, the rate of radiation is 4th order of temperature, the rate of convection, conduction are all 1st order. So, it really heats up faster, radiation heats up really fast, it also cools really fast. Okay. So, when there is radiation this is very hot. So, therefore, the air closer to the surface is hotter than air above. So, you are expecting to see this kind of a gradient in the temperature. What happens when there is no radiation, say at 7 p.m., 6:30 or 7 p.m., sun is set, no radiation, what then starts happening? The soil then starts cooling, it cools very rapidly, it has given up all its heat. Then you see a certain small decrease, the temperature, the air is still hot, but the soil has started cooling. So, you start seeing this kind of behavior. Now, the air is warmer than the soil has cooled down really fast, and you have heat transfer is occurring in the reverse direction, and this is slower process than radiation. So, as you go deeper into the night, you are likely to see this kind of behavior well into the night. Then when you have morning, 6 a.m. or 7 a.m. sun rises, this starts going reverse, because now you may start seeing things like this. The reverse is happening, the land starts heating up very quickly, and it then starts heating the air on top of it. So, the gradient starts moving this way. You are following? You can see it very clearly when you have in winter conditions, extreme winters, when you see fog in places where there is fog that happens. You can see that in the daytime you do not see any fog. In the night time the land cools very rapidly, and if the conditions are humid and it is amenable for fog formation, fog forms near the surface. Okay. But the moment sun rises, what do you see? when you see fog formation, we have this term called lifting of the fog. How many of you have seen lifting of the fog? What it means, what it looks like is the surface is full of fog, then suddenly the land will clear. The fog looks like it is going up, it is clearing up from the surface. It is clearing up because of what is happening here. Right next to the surface, land is heating up, air is heating up, all the water droplets, fog is water droplets, liquid water droplets, they are evaporating and there is no more particle there, it is all vapor phase, it is clear. But the regions above are still heating up, it is taking time. So, it is happening slowly, it is happening by conduction or convection or whatever the process is. If there is no wind, there is no convection, it is conduction mainly. So, it happens very slowly. So, this profile, this is called as what is called as an environmental lapse rate. The lapse rate, it's called as a lapse rate because it's a temperature profile as a function of height. The environmental lapse rate varies from place to place throughout the day, season to season. So, every day you go, you will find some profile. Right now you will find a profile, tomorrow morning you will find a different profile, but by and large this is seasonal. For a place like Chennai, environmental lapse rates are generally known. So, the people have been measuring it for a long time, they know that this is what will happen, this is what will happen, this is the general lapse rate and the temperature profile goes in some direction. Yeah. Now, this is what is happening in the system. So, this region is called as the inversion, the temperature inversion. This temperature inversion means in the daytime temperature is reducing as a function of height, but here temperature is increasing as height. This is called as an inversion. Okay. Now, we will see why this inversion is important from the point of view of pollutant transport. So, in this system, this is the environment, this is how the environment looks in terms of temperature. In this system, if I drop a parcel of air coming from a pollutant source, for example, if I have an engine, if I am running a diesel generator or something in the middle of a field, what will happen? So, it is generating some gas at some temperature and you want to see what will happen to this gas, to the air parcels. So, I am taking the case of an engine or something because it is releasing like parcels of air at given intervals. Okay, let us say puff, releasing a puff of air, and so we can see what happens to it. So, several things can happen to it depending on what is the condition in the environmental lapse rate. Okay. So, what will happen to a parcel when it is released? So, normally if I release a parcel here, it is expected to follow. What happens is, if its temperature is higher, it is going to want to go up. So, two things are at play here. One is buoyancy is making it go up, but as it goes up, if there is no exchange of energy, its volume also expands like this and it cools. So, it is cooling and expanding, two things are happening, and the rate at which it is cooling and expanding, it is called, if it is assumed to be dry and adiabatic, it is called as the dry adiabatic lapse rate. It is an ideal number. The reason we assume it is adiabatic is there is heat transfer. What it means by adiabatic is there is no heat exchange between the surroundings and this parcel. This parcel is just behaving, energy is conserved inside, but because it is moving up because of buoyancy, as it goes to a slightly low pressure area, it expands, and the volume expands and temperature drops and so on. So, the temperature of this parcel is changing as it is going up and it is changing in this fashion, and this can be derived by using thermodynamics and statics. I will give you the derivation, we will not do it in class, but I will put it there in your notes. It's very simple derivation, it is called as dry adiabatic lapse rate. What it assumes is the air is dry and there is no heat transfer. The adiabatic part of it is in the assumption that it moves fairly fast between one position and another position, so there is not enough time for it to come to thermal equilibrium with its neighborhood. So, it is always moving fast. It may not be true, okay, but it is a nice reference point for us to have, and it is given by the symbol gamma. We call it as gamma adiabatic. this is expected to be the trajectory this particular any air parcel it will take, and the value of dry adiabatic lapse rate is minus 9.8 degrees centigrade per kilometer, which means that irrespective of what the starting temperature of this is, it will cool in this fashion, which means I have a air mass that is at 400 Kelvin, I have a air mass at 350 Kelvin, all of them will go in the same direction. The delta T by delta Z is the same. So, now you can imagine if I superimpose this is the trajectory of a pollutant. This will what the pollutant will do because of its initial conditions. If I superimpose on this environmental lapse rate, what will happen to the air mass is what is the consideration. So, we will quickly go to the this is what is called adiabatic expansion and cooling. This is what we just described. There is a term called atmospheric stability that that comes into play. So, what we look at is the following. So, this is adiabatic lapse rate, and so let us assume that this gamma environmental is the environmental lapse rate, which is the environmental change in temperature of height as in the environment that is existing at that particular time, and gamma adiabatic is the trajectory this wants to take. So, let us say at this point of intersection, this particle is this gas this thing is moving up naturally, but there is a point where it intersects with the environmental lapse rate. Now, with some mechanical turbulence, say it is here and I push it up a little bit, and that force that is pushing it up is mechanical force. There is always wind on top of all this, so the wind is pushing it up. If it goes up, what will happen is, when this goes up because of wind, the temperature of this parcel is always going to be higher than the environmental, than its surroundings, which means it has higher, greater buoyancy and it will continue to go up. In the same way, if I push it down, the temperature of this parcel is always lower than what its surrounding is, so therefore continue to go down. So, it is an unstable situation. It is like this, if I am balancing it, this pen here, if I am correctly balancing it, and then this is a, but if I tilt like this, if you see, if I tilt like this, it is stable, it is going back to its original position. Suppose I am here and somehow I am balancing it, if I am giving it some force, which means I am removing this, it will fall down. If I am balancing it here, if I remove it, it falls down, it continues in this direction or in the other direction. So, that is called as unstable. Okay. So, the unstable environment, in the presence of mechanical forces, turbulence, the way in which the thermal forces are, the temperature gradients are, it accentuates, it exaggerates the motion of a parcel in the direction in which its mechanical energy is pushing it. So, you will get extremely large movement of the pollutant masses depending on how the wind is. So, the wind and the thermal forces exaggerate, add to the already existing mechanical turbulence in order to create a situation. It is called as unstable. There is another thing which is called as this neutral, in which the lapse rates are similar. So, in which the temperature profile of your parcel and the surrounding are always the same. So, the temperature has no effect, the buoyancy has no major effect on the movement of this parcel. It is a wind, mainly the wind is determining whether it goes up or down. So, if the wind is very high, it will go up or down, that is all, because the temperature is the same. There is no extra turbulence, there is no extra thermal inducement to parcel movement. So, this is called as neutral. If you have a system like this, if I push it, the environmental lapse rate is this bold line, and this is the dotted line is the adiabatic lapse rate. So, pollutant is supposed to go there. So, if I move it here, what happens is it goes up, but when it goes up, the temperature, its temperature is lower than that of the surrounding environment. So, its buoyancy is greater. So, it comes back down, the density will be greater, it comes back down to the original position. Same way here, this temperature here, the temperature here is higher than the surrounding temperature. So, it will want to go back to this point again. Here again this temperature is lower, and therefore, the buoyancy will drive it back to this point, which means it is very stable. So, this is stable and it is usually caused by inversion. Inversion causes this kind of behavior. Okay. Among all of these, which do you think is, from a pollutant, from a concentration perspective, which do you think is more favorable for air pollution? Whether stable, neutral or unstable. What would you want for pollutant concentration to be low? You want pollution concentration to be low. Unstable. You want it to spread as far as possible, because from the box model point of view, if it is spreading far, which means it is able to spread far, which means that dimension of that z dimension is very large. In the case of an inversion like this, it is not going anywhere, it is contained within that. So, for example, if I release a pollutant here, it is going to go up until this point and stop. Okay, the inversion is there, it is going to stop. So, if I keep on releasing, this essentially makes a ceiling to my pollutant concentration. And so, if I keep on releasing here, this concentration here in this volume is going to go on increasing, and therefore, that influences the concentration. So, this is the direct reference to. So, if you have an unstable environment, this height is very high. It has the opportunity to mix in a larger volume, and therefore, the concentration of rho A1 is going to be smaller in the case of an unstable environment. In neutral, it depends on how the wind is taking it. There is no real indication as to how far it will go, it depends on the wind alone. Okay. So, this is the definition of what people call as a mixing height. The mean mixing height is the intersection of the adiabatic and environmental lapse rates. So, the environmental lapse rate is known at different times of the day. If you know what the temperature of your pollutant is, you can calculate where is the adiabatic lapse rate. So, adiabatic lapse rates can be anything, it can be here, it can be here, it can be anything. It depends on what temperature is your at the ground, what is it, where are you releasing at what temperature is the release happening. So, there is a particular location where you can have where the mixing will happen, mixing height will be there. So, one of the things that people, the way they also look at it is from a long term perspective. It is very laborious, very stressful and very difficult for everybody for every source, it is difficult for us to get how far it is going to go, right. We are in a mixture, we have a lot of pollution sources, all of them are releasing at the same time, and we would like to know what is going to be the average mixing height, so that we can predict what is going to be happening downwind, those kind of things. Okay. So, there are some general rules people use in order to do this. We will see that in one of the illustrations, problems that we, but so therefore, for that reason there are mixing heights that are determined for a particular location for a particular season based on the pollution profile in that region. People already know, have some idea as to how this looks like, and they use that number in order to do modeling of atmospheric pollutants and that kind of. So, mean mixing height is reported for different locations and it changes with and so the this concept of stability and mixing height is very important when we are looking at pollutant transport in the atmosphere, when we are talking about atmospheric dispersion. So, what we say about dispersion is this is a visible phase of dispersion. So, there is a source, this is called as a stack, this is a general atmospheric dispersion jargon. This is a stack is any source, but it is a very classic stack. So, you can see that there is an emission occurring here, and you can see that it is spreading, you can see a very classic, this is spreading, and this is spreading because it is spreading in all directions, it is spreading in the x, it is of course moving in the x direction because there is a wind that is pushing it in this direction, there is wind in this direction, but it is also moving up a little bit. Here you can see that it is moving up a lot, it is generally moving in this direction, but it is also going up a lot. So, this vertical dispersion and this horizontal dispersion, this y direction, in the y direction also it disperses. The extent to which this happens determines what will be the concentration in this region. So, this pollutant mass is enclosed in this, you can see it very clearly, it is not gone out of this region, it is here, unless I can't see. So, sometimes you can't see this, it's an invisible thing, you can't see any white stuff coming out, because this white material is because of two reasons. Either it's water vapor, it's condensing, or it's particulate matter. It's some particulate matter which gives it some shape and color. So this boundary is known as a plume, it's called as a plume. So this plume, the shape of this plume depends on how much it is spreading in both directions, in the x and the y, and that depends again on whatever we discussed. The two things, one is the convection because of mechanical forces, which is the wind, and the convection because of thermal forces. So the thermal forces essentially influence the vertical spread, and the mechanical influences both vertical and horizontal. So if there is no mechanical force, there is no wind, nothing will happen, it will just sit there and it will grow. So imagine there is no wind, if I light a fire here, you will see that it will just grow like this, and it is only diffusion process that is happening and buoyancy that is happening, no other convection is happening. The temperature is only moving, the mass is moving by buoyancy, and buoyancy also stops at some point, there is it comes in equilibrium, it will just sit there and it will move slowly by diffusion. So we will look at all that. So we will stop here today.